Hi, everybody. We are now going to see non-context-free languages. So let us first try to develop some intuition on when a language may be context-free and when it may not be. So if L involves regular expressions, then we know it's context-free. We saw this earlier. But also, if it involves nested matchings, then probably the language is context-free. What is a nested matching? Well, there is no clear-cut definition. This is just intuition. It's a rule of thumb. But in a language like 0 to the n, 1 to the n, I can match the zeros with a 1 without overlapping my lines. Okay? If I cannot do that, it means that the matching is not nested, and then it is probably not context-free. So, for example, a language like WW, so the concatenation of the same string, is not context-free because intuitively this one here has to be matched with this one here, but then this one here has to be matched with this second one here, and I will have a crossing here, which means it's not nested. And similarly, a language like 0 to the n, 1 to the n, 2 to the n, which seems very similar to this previous one here, is actually not context-free. Well, because this 0 has to be matched to these two here, and this 1 as well has to be matched here, so you will have a crossing. Turns out there is a pumping lemma even for context-free languages. Okay, it's similar to the one for regular, but it's a little more complicated because you simultaneously pump strings in two parts. So you write W as U, V to the I, X, Y to the I, Z, and you pump both the V's and the Z's, both the V's and the Y's simultaneously. So here is the pumping lemma for context-free. And as before, we have some stuff in the box. And the pumping lemma says that if L is a context-free language, then the stuff in the box is true. The stuff in the box is just like before, except that instead of decomposing just as XYZ, we now decompose with 5 variables, U, V, X, Y, Z. We write, as I mentioned earlier, W as U, V, X, Y, Z, where the length of Vy, these two things that you'll pump, is non-zero. The length of Vxy, the middle part, is the most P. And for every I, when you pump Vi and Yi simultaneously, you obtain a string which is in L. What is the proof idea for this? Well, we are just going to sketch it, but let's say that you have a language which is context-free. Let's consider string W in L, which is very, very, very long, okay? Now, since it's so long, the derivation has to repeat a variable. This is similar to repeating states in the pumping lemma for regular languages. And Vxy would be the piece of W that is derived by the variable. And because V was repeated once in the derivation, you can repeat more than one time, obtain new derivations of other strings. Okay, so S derives some variable V, which derives some stuff, and then it also derives itself. So you're going to have some stuff on the left and some stuff on the right, and then derives here. So then I can repeat this portion here, okay, to put more copies on V and get more stuff here, more stuff there. And this is the V part and Y part that you're pumping simultaneously. Like before, the pumping lemma is not useful to prove that something is context-free. It is only useful to prove that something is not context-free. And for that, we use the contrapositive. Okay, if L is a context-free language, then A is true. Is the same thing as saying that if not A is true, the stuff in the box is not true, then L is not context-free. And the complement of the stuff in the box is now this. Okay. To prove that L is not context-free, it's enough to prove not A. Not A is the stuff in the box. And again, we can think of this as a game. These are the rules of the game. Okay. So the adversary picks P, you pick W of length at least P. Now the adversary decomposes W as U, V, X, Y, Z, where the length of Vy is non-zero and the length of Vxy is at most P, and you get to pick I at least 0. And finally, you win if U, V, I, X, Y, I, Z is not in the language. You can win this game, you prove the stuff in the box, which means the language is not regular. Okay, let's see an example. I'm going to prove that this language A to the N, B to the N, C to the N is not context-free. Okay, so the adversary moves P. Now you get to make a move and you have to pick a string, and no, with the hindsight, you're going to select a string A to the P, B to the P, C to the P. And the adversary moves, picks a decomposition, U, V, X, Y, Z, with those rules that it has to satisfy. And we make the move I equals to 2. How do I pick I equals to 2? I don't know. You can always try equals to 2, you can try equals to 0. With experience and practice, you will figure out. So we have to show that U, V, V, X, Y, Y, Z is not in L. Okay. So the first observation is that the Vy misses at least one symbol in the input alphabet. And why is that? Can you figure out why that's the case? That's because between the A's and the C's, you have PBs, and the length of Vy is at most P. Okay? But if that's the case, what happens to U, V, V, X, Y, Y, Z, the pump string? How can we conclude the proof? Well, this is going to have too few of that symbol. That symbol is not being pumped, but some of the others are, so it's not in the language. Done. Okay, let's see another example. Now we pick A to the I, B to the J, C to the K. We claim this thing is not context-free. The adversary moves P. Again, we pick a decomposition. We pick a string, and we're going to pick the same string as before. And the adversary picks the decomposition. So far, it's the same proof as before. But now we need a few cases. The choice of I will not be fixed. Just like in chess, in a chess game, the move that you make will depend on the move of the adversary. I can't just pick an absolute choice like I go to 2. This is a setting in which things get a little bit more complicated. Our choice of I will depend on the decomposition, on the move of the adversary. Okay? So where do we stand? We have W is the string here, this decomposition, and we have to pick I and show that this pump string is not in L. Okay? So now we do a few cases. One possibility is that there is no A's in Vy. Okay? Somehow the adversary picked a decomposition in which there are no A's in Vy. Okay? So what do we do in this case? Can you guess? Well, we can just pick I equals to 0. We erase V and Y. Because there were no A's, we are removing some side stuff like B's or C's. So now you have fewer B's or C's than A's, which means the string is not in the language. Because note that the number of A's is at most the number of B's, and the number of B's is the most the number of C's in the definition of the language. Okay. So if there are no A's, I'm done. What if there are no C's? If there are no C's? Well, then you can pump up, right? Then you pick I equals to 2, and you pump, you're pumping either A's or B's, and you're gonna have more A's or B's than C's. Okay? Now, what happens if you have no B's in Vy? What happens now? This case is slightly more complicated. Well, in this case, you fall into a previous case, okay? Because the length of Vxy is at most P, which means that if you don't have B's, okay, you either don't have A's or don't have C's, okay? You have A's and B's and C's. If you don't have B's, the stuff that you're pumping must be all on one side, all C's or all A's. So you fall into a previous case and you're done. Okay, let's now do an example, the language SS, where S is a B string. The adversary moves P, and we're gonna, with the benefit of the hindsight, we're going to move the string, we're going to pick the string 0 to the P, 1 to the P, 0 to the P, 1 to the P. Note, when we did the proof for regular, to prove that this thing is not regular, we actually moved 0 to the P, 1, 0 to the P, 1. But that move will not work for context-free languages. Okay? That move will not work for context-free languages. So we need a different move, and the move that we make is this one. Okay? We'll see in a second why the move works. Okay, so the adversary picks a decomposition. Now there are three cases. Vxy is in the first half of W. Okay, it all lies in the first half of W. Then what do? Think about it. Well, then the second half of Vxyz starts with 1. Right? So what does it mean? It means that this is my string. You have a bunch of zeros, a bunch of ones, a bunch of zeros, a bunch of one. This is the middle of the string. Okay. Now, if I'm pumping just in the first half of W, it means that you're pumping here. Okay. When you pump here, this middle point will move a bit to the left. And so the second half of the pump string will start with a 1, but the pump string still starts with a 0. And this is impossible because this was supposed to be the language of SS. Okay. Now, what happens if Vxy is in the second half of W? Well, then the first half of the pump string ends with a 0, but the pump string still ends with a 1. By the reasoning is similar to before, symmetrical, and you get a contradiction. Okay, but maybe that's not the case. Maybe Vxy touches the midpoint. Okay, maybe actually you're pumping something which touches the midpoint. What happens in this case? Can you guess? Well, then we can pump down. I'm going to pick I equals to 0 and obtain a string uv0 xy0 xy0z, so just uxv. Now, this string here, I've not touched the 0 to the p or the 1 to the p because I was in the middle. So now I've either pumped down these ones or pumped down these zeros. If I pump down the ones, you will not match this. If you pump down the zeros, you will not match that. So either way, you're not in the language and you're done. And that concludes the overview of non-context-free languages, and I'll see you next time, in which we're going to study a very cute context-free problem.